Hey guys, my name is Patrick, and today I'm going to be talking about magnets. Now we all know the simple idea of a magnet. You know, there's one end of the magnet that is positive, and there's one end that's negative. Now the simple rule of magnetism is that opposite charges will attract. So if you have a magnet that has a magnetic field of positive charge, it will want to stick to a magnet that has a charge of negative charge. Now, the way that this works can be shown like this. So I have a magnet, to say, of X charge, and then this magnet right here has two ends of X charge and negative X charge. So we can just, if I put this magnet closer towards the magnet right here, you can see that this magnet is pushing away. So if I just keep this in like that, it's pushing away. See it like that. But if I just flip this magnet, it's going to want to stick to this magnet, because now I've changed it from this positive magnet and this positive magnet on this side, on the red side, them wanting to push away, to this positive magnet and this negative magnet. They're going to want to stick together. Now watch. See how it came like that to my hand? I'll show you again. Now this is the simple idea of how a magnet works. Opposite charges will attract. Now, but what if I could use a magnet to attract something that is not magnetic, such as water or cereal? That'd be really interesting, because you could really blow people's minds by saying, "Oh, look, I can use this magnet to take your cereal away, or spill your water," which is something that you do not see every day. So this effect is called diamagnetism, and it's what I'm going to be explaining today. Alright guys, now I'm going to explain what diamagnetism is. So the basic idea is that every single object has some diamagnetic property. It ranges from perfect diamagnetism, such as a superconductor, to almost none, like cereal or wood. But there is one substance, like water, that is kind of a mediator in between those two. It has some diamagnetic property, and it's widely accessible. So it's really easy to see this property in action. Now, the way that this works is that whenever you apply a magnetic force onto the object, such as water, the electrons in the H2O molecules will align in such a way to repel that magnetic force applied. So as you can see here, there's a magnet, and its magnetic field is drawn around it. This is not actually what a magnetic field looks like. These are just the forces shown. And here is the surface of the water. And as you can see, when the magnet is placed near the surface of the water, there's a small dip in the water. And this is because water, being a liquid, can move easier than a solid. So if you're holding the magnet there, it's not like the water's going to push your hand back up, because it's not that strong of a diamagnetic force. So the water in turn will dip just a little bit under the magnet. So if I was to have a bowl of water right here, and here's the water, and I place a magnet right here, there'd be a magnetic force applied down onto the water. So what would happen then is, right under the magnet, there'd be a dip, like I said. So the way you can see this happening, there's two ways. The first way is to get a very strong light beam and try and refract that light beam off the surface of the water, and you can see a slight distortion in any image you place next to the water, because of how the light is bounced off of that water. It's not a flat a flat surface of the water. So the image that you place behind the water will be slightly distorted. And that's the first way. The second way is to place a small floating object right on the surface of the water, so that whenever you place the magnet right over the water, the dip will cause the object to kind of go down into the dip. So like this. So the object will go this way, and you can even stretch this further by saying moving the magnet to either the left or the right, or forward or backwards, any way you want, and that dip in the water will move accordingly. And along inside that dip, so now that the object is in this dip now, our magnet's up here applying the force. Whenever you move the magnet to the left or to the right, the object will move with the magnet because it is caught inside of this dip, and it itself doesn't have enough mass or velocity to escape this little wave break right on the edge of this dip. So it'll stay inside of the dip itself, and you can move the magnet all around the water, and that object will follow. This is a pretty cool thing to see. And yeah, so that's basically how diamagnetism works. I'm gonna go show you how it works in person. Alright guys, so today I'm just gonna demonstrate the effect of diamagnetism on water, just using this little piece of cereal right here. I'm just gonna use this so you can see it as like a visual piece to the motion that is caused by the diamagnetism effect. So before I do, I'm just gonna explain that. I'm just gonna put a piece of cereal in water, and I'm gonna place this magnet right here over the piece of cereal, and it should move the piece of cereal wherever I move the magnet. So let's just try it out. It's actually pretty cool to see. So as you can see, it's water, and I'm just gonna let the motion of this piece of cereal stop for a second so you guys can see that the magnet actually is causing the motion. All right, here we go. As you can see, I can move it left. I can move it back right. It's a pretty mind-blowing effect. Yep, pretty mind-blowing right there, as you can see. It's blowing this kid's mind. All right. So that was the effect of diamagnetism. Alright guys, now I'm going to explain what we just saw. So by me putting the piece of cereal in the bowl, like this, and by placing the magnet over that piece of cereal, the magnet applied a magnetic force onto the piece of cereal. Not really onto the piece of cereal, onto the water. And that caused the water to, in turn, dip down like this. Because by me not moving and the forces applied, something had to give, being the water. Now, why this actually happens is because the electrons moving around the hydrogen and the oxygen in the water molecule, those are either sped up or slowed down by me applying the externally applied magnetic force. And by those speeding up or slowing down, they can arrange themselves in such a way that allows the water to slightly kind of bounce the magnetic force back onto the magnet, which is what caused it to dip. So whenever I move the magnet to the right, the dip would follow, thus causing the piece of cereal to follow as well. Now I want to emphasize that all substances have the diamagnetic effect. It's just only some can show it, such as water. Another object is called a superconductor, and this is known as the perfect diamagnetic substance because it can almost perfectly reflect the magnetic force applied. So much so that if you place a magnet over a superconductor, it can levitate that magnet because of how well it is bouncing that magnetic force back onto the magnet. It's a pretty cool thing to see, and I'll throw a picture towards the end of the video. I just want to thank you guys for watching. This is the Diamagnetic Effect.